Swayam Prabha. Digital India. Educated India.
So, welcome back. Today I am going to start with induction machine, and I am going to do induction machine in two ways. So one way is going to be based upon the way we did the single phase and the two phase machines, derivations based upon energy, co-energy, torque, relationships, and equivalent circuits from there. So, this I would like to call this as a very formal approach, very elegant and formal, elegant, but somewhat cumbersome also, in the sense that you will have to handle 3 windings on the stator, 3 windings on the rotor. So, your matrices will become 6 by 6 matrices, and then your arithmetic would involve that, sine cosine manipulations would involve that, and so it will be a bit more cumbersome. Another alternative is that after you have done everything, basically you realize that you can treat a induction machine, and an induction machine can be a generator, induction machine can be a motor. So, most of the times most of the common applications are induction motors, they are the workhorse of the industry, but then wind farms use it as a induction generator also. So, therefore, you have both applications today as induction generator and induction motor. So, the point is we can treat this induction machine as a generalized transformer. So, we can treat the induction machine as a generalized transformer, and then derive equivalent circuit, from there, and from the equivalent circuit you usually derive the torque speed characteristic of induction machine. So, this is a bit empirical, it is not incorrect, it is bit empirical, not that it is not that rigorous as it is not that rigorous, it is rigorous enough, but it is not that cleanness, that transparency in the derivations that you see in the energy co-energy approach, that transparency you do not sort of see it here straight away, but it is simpler. It is simpler to teach and probably easier for you students to assimilate also. So, what I will do is, what I am planning to do is, I will first do it using the second approach. I will take the approach of generalized transformer, and then time permitting I will also do the energy co-energy approach. So we want to take this thing that once you have understood the energy co-energy principles and found out ways to develop torque from there, then you can do relays actuators from there, you can do single phase machine from there, you can do two phase machine from there, you can do three phase machines, the synchronous machines and other machines from there, and then you can also do induction machines from there. So, it becomes a very generic kind of holistic thing, and that is something which I like about it. I have not seen it really taught done in that way in many books. Professor Pai's book is only clearly based on this line. Many other books usually take each machine separately, like MG Say or Fitzgerald Kingsley of course does energy co-energy principle, and so you get the mix, and I think as a mature student you should probably try to see it both the ways. Okay, so we are talking now of three phase induction machine, and our first question is how is it a generalized transformer? That is our first question, and how it is a generalized transformer. So let us first understand induction machine itself. Let us try to understand the induction machine itself. So what I have is a rotor and a stator. So let me duplicate this. So I have a rotor and a stator, and you of course know that this is the air gap here, this is my air gap, and you can think of three coils. So usually I show the I show it like let me show it on the stator first. So this is my stator, this is my rotor. I do not show all the slots and all that, but you know that they exist. So this is my A, this is my A dash, then go 120 degree further here, you get B, and you get B dash, and go 120 degrees further here, 60 and 60 on the both sides, and you get C, and you get C dash. So you can think of it, these are of course strictly speaking distributed windings, three phase on stator, and if you want you can show it like this. This is 120, and these are the A, B, C windings distributed in space, usually shown like this, which represents stator, and let us put using another color the three rotor windings. So assume that I'll place I want to place them with some displacement. So let us say this is A, but in my mind I find it difficult to imagine the A dash displacement. So like say 10 to 15 degrees further rotor on the rotor. Then on the B something will come here and something will come here B dash, and then on the C also I will have to advance, and then I have to go diametrically opposite here, and I will get C dash B dash. So, it is like sort of saying that I take this picture, copy, paste, and like for example, I have just rotated this picture, so as to keep my things clean. Now, the stator and the rotor are basically. So, first take that you understand now what I have taken is, we have 3-phase distributed windings in space on stator, which would be connected to a 3-phase supply. So, the A windings will be connected to A phase supply. Let us call it as say V of A of t is equal to V m cos of omega s of t. B phase would be connected to B phase supply, which is V b of t equal to V m cos of omega s of t minus of sine or cos something like that 2 pi by 3. Okay. I will see whether I want sine or cos very soon. Right now, just for that sake of continuity, V m cos of omega s of t minus 2 pi by 3. Now, you know that V is equal to d lambda by dt. So, phasor wise V phasor is usually j omega times the flux linkage phasor. I am talking of Faraday's law. So, the flux phasor lags the flux phasor lags the voltage phasor by 90 degrees, and I want actually my flux phasor to be cos of omega t for my sake of discussion. So, what I will do is I will add plus pi by 2 here, I will add in plus pi by 2 here, and assume that I am taking voltage phasors like this. I am taking voltage phasors like this. So, what it is going to do is, it is going to say that lambda A will be equal to lambda m cos of omega s of t, lambda B the voltages, the fluxes, steady state fluxes will be lambda m cos of omega s of t minus of 2 pi by 3, and lambda c would be lambda m cos of omega s of t plus of 2 pi by 3 or minus of 4 pi by 3, whichever way I want to connect this. Now, 3-phase winding connected distributed in space, which would be connected through to a 3-phase AC supply. Consequence of it, that it creates rotating MMF wave, something we have seen in an earlier lecture also. Without doing again the derivation, we will recap. This is basically the idea, that when the 3-phase distributed winding on space is connected with a properly phase sequence of ABC, connected to 3-phase distributed 3-phase power supply, which is 3 phase supply in time, then you will get a rotating MMF wave, which you can basically visualize as a, which basically you can visualize as a north-south magnet which is rotating at the synchronous speed. So you can visualize it like that. Now, this idea that you are able to create a 3 phase rotating magnet without actually having a magnet there, from the stator side basically means that if on the rotor something similar is done, then it would try to latch on with the it will try to latch on, like suppose it had the rotor had just a piece of iron, no magnet for the time being. This it will feel attracted by this magnet, and so it will try to latch on and try to rotate in this direction. So for that purpose, what we have in an induction machine is a 3 phase winding similar to stator, but the number of turns will be usually different, right, similar to stator. Say this will have NR turns, if the stator 3 phase winding in space has say NS turns, then this would have NR turns, and similar to stator and NR turns, and similar to stator and mounted on rotor and short circuited. We are going to come to this reason why it is why are these windings short circuited, but very similar 3 phase windings like what we had on the stator, but now short circuited. And you know, you have already discussed this distributed windings, actually just a footnote, so to say. This NS actually number of turns and NR number of turns, because they are distributed, you will effective number of turns due to winding factor etc. will be Kw1, say Kw2 will be bit different. So, it is not just the actual number of turns, but the effective number of turns that we should be talking about with respect to the stator and also with respect to the rotor. So, but we will continue to use NS and NR, but just keep this at your back in mind, like unlike a transformer, these turns are distributed in space. So, each of the coils, even when they are connected in series, each of the coils has voltages which are slightly phase displaced. So, when you do the effective summation of the voltages, that effective voltage is not just n times the voltage of a turn, but rather has to be reduced by according to the winding factor of the that we have talked of in our earlier lectures. Good. Now, can you make a connection with the transformer here? You may find it a bit difficult to write immediately, but can you make a connection with transformer? So, for that reason, what I will do is 3 phase transformer. I am talking of a 3 phase transformer. So, let us assume that stator is windings are star connected. They could be delta also, I have no problem, but whenever we talk of 3 phase transformers, we talk with respect to star or delta connection. So, for the sake of simplicity, let us say stator windings are star connected, rotor windings are also star connected, and short circuited. Now, when you also to make a analogy with the transformer, let me assume that rotor is held fixed at one location. That means, I am for the time being holding on to rotor, not allowing it to rotate. Later on I will let this go and then it will be rotate. So, from transformer I will go to generalized transformer, where the transformer will also has a freedom to move in space. See, the the transformer 3-phase windings that we discussed earlier in the course, power transformer 3-phase windings, actually they are also distributed, is it not? I mean, nobody is concentrating them. You have 3 limbs in a core type of transformer and then you wind it like this, so it is in space, then the other one that is also in space. But the geometry is not a circular geometry. The distribution in phase is not to create a 3-phase rotating MMF wave, because there is no rotating MMF wave or of any kind which is created. Then you do not talk of something trying to move and all that kind of thing. So, the distribution is just vertically sort of distributed in space. It does not create any real force or torque for it to rotate or anything like that, and it just works as a simple plane transformer. But here what has happened is the 3-phase windings are distributed on space around a circular region, and then they carry 3-phase voltages or currents. So, it causes a rotating MMF wave, and if there is a rotor sitting here, let us say a piece of iron like that, it will try to align itself with that rotating MMF wave and try to just rotate. For the timing, there is not even any winding, just a piece of salient construction of a iron, and you can see that it will tend to rotate. But this is not a salient construction of iron piece that is there in an induction motor. Instead, what you are having is another circle embedded, very symmetric, and 3-phase windings connected on that and usually short circuited. You could connect it through you could have those connections going into a resistance, or you could have a connection going into another supply, doubly fed and all that. That is for later discussion, that is not for now. For the simple discussion, first discussion, these 3-phase windings will be just short circuited. So, you do not have any access to the rotor, you just mounted 3-phase windings on that, short circuited them. So, what I did basically is these 3-phase windings here on the rotor. So, this is connected to this, I said star connection. These terminals are what are available outside, and I just short circuited. So, this short circuited whole thing assembly has a degree of freedom to rotate, and you right now you do not have any control on there. This is connected to VA, this is connected to your supply VB, and this is connected to your supply, this is connected to your supply VC. So, the 3 windings are connected like that. Okay. Now, now the next question is, if I have held the rotor stationary, that means I have not allowed it to rotate, and I have created a connection something like this, which is shown in this figure, 3-phase winding on this 3-phase. Is this a 3-phase transformer? Can I treat this? The question I am asking is, can I treat this as a 3-phase? Can I treat this as a 3-phase transformer? Actually, I would want to wait and see your reaction, really speaking, in a class, whether you would agree to me or disagree with me. But you know, because we are in this instruction of medium which is online, I have to just answer it as yes, indeed it is to be seen as a 3-phase transformer, because you have coupled windings. For the time being, just assume that, to make your life simple, just assume that this alignment was exactly like this, no, the two windings were exactly. So, A dash here, the A was here and the A dash was here, the B was here and the B dash was here, and similarly for C. So, effectively so effectively I had effectively I have just them. So then what happens? You can see that there is a strong mutual coupling between this to this. You will have mutual coupling bits to this. They are exactly, their mutual coupling axes are are aligned, and so you can just think A dash as one transformer, B dash, sorry, I mean A dash of stator and A dash of rotor as one transformer, single phase transformer, B dash of stator and B dash of rotor as another single phase transformer, and C dash of stator and C dash of rotor as the third single phase transformer. The stator windings are connected to the supply, and the secondary windings, which in the secondary primary windings are the stator, the secondary windings are the rotor windings, and the rotor windings are short circuited. Right now I have both of them in YY configuration. So you can map that, actually yes, it looks something similar to the transformer. But here there is some additional thing which we will see it much more clearly when we do the energy co-energy based discussion. There is a mutual coupling between in single phase transformer also, in three phase core phase transformers also it is there. There is a mutual coupling between the A phase windings and the B phase windings and the C phase windings, because if this is the A phase winding, flux here will break, and just excited alone it will break once in the B phase, once in the C phase. Then B phase winding, the flux will be here, will break into this, so mutual coupling, and C phase again break into this and break into this. So mutual coupling is there, but we usually think of them as three single phase transformers, primary, secondary, and just connecting them in star delta configuration. The two are equivalent, we have seen that earlier. So similar discussion, similar similar story, so to say, applies here. There is a look from mutual coupling perspective. It is not just A to A, I mean A to B to all kinds of, it is a 6 by 6 matrix. We will be getting to that 6 by 6 matrix later on, and the net under balanced condition of operation, the net mutual inductance, effective mutual inductance, all that we will be getting later on. But right now, for the sake of our discussion and simplicity, what we have is essentially, now rotor is held still and I have aligned the rotor windings along with the stator windings. So, it looks very similar to three single phase transformers connected to a three phase supply on the primary side and short circuited on the three phase secondary three phase windings, which are star connected, and then short circuited. The next question that will be there in your mind, the next point which is going to be there in our mind, then is, there was no air gap. There was no air gap in three phase static transformer. I am now using a word called static transformer, but there is an air gap. There is an air gap in the induction motors windings. That means, if I have A dash of the primary, if I have this A dash of the primary winding and I have A dash of the secondary winding, there is a intervening air gap which is there, which was absent altogether in the static 3-phase transformer. What are the consequences? Consequences are, what are the consequences? The consequences are, one, that reluctance will be lowered, the reluctance will be higher, reluctance will be higher due to the air gap. Due to the air gap, the reluctance will be higher in the mutually coupled path. Reluctance will be higher in the mutually coupled path. Consequently, mutual inductance, or more like in talking in terms of the parlance of the transformers, the magnetizing impedance or inductance or reactance will be lower. So, if you recall the transformer equivalent circuit, if you recall the transformer equivalent circuit, this is the this is the leakage this is the primary winding reactance, this is the leakage reactance of the primary winding, and this is the magnetizing impedance of the winding. So, actually all of this put together, and Rm accounts for hysteresis and the core losses. R2 dash is the resistance of the secondary winding referred to primary, X2 dash is the leakage reactance of the secondary winding referred to primary, and this ZL dash is the impedance, which any variable impedance which is connected to, and this is my supply, and this one is also referred to primary. Now, here this Xm used to be a very large number. So, I had said that as an approximation you can move this thing here, and then I said that when you are connecting studying a system like a power system or an energy system where there are thousands of interconnected transformers in the grid, because this current is only 1 to 2% of the full load current. So, even this branch could be ignored, and you get just a simple equivalent circuit in which you have this as R1 plus R2 dash and this as X1 plus X2 dash, and even this simplest for the study of voltage regulation and other aspects, even this simple equivalent circuit is good enough. But in case of induction machine, we will not be able to do this. We will not be able to move this. We will not be able to move this to this side, because this inductance is much lower. So, there is going to be appreciable current flowing here, 30 to 40% of the full load loss or full load current or something like that. Even when this is open circuited, just to set up this through a air gap, significantly larger amount of current is required, and therefore, if I move it this side, it will alter these voltages significantly. I am going to get to a equivalent circuit which is something similar to what you are seeing here. To recall, I have put up this transformer equivalent circuit for you, but what is going to happen is I will not be able to move it on this side. The second thing is this Rm also will not be, you will not see this in the induction machine's equivalent circuit, because if the rotor is rotating very close to the synchronous speed, if the rotor is rotating very close to the synchronous speed, then the hysteresis and eddy current losses will be much smaller and you could account for them separately. So, therefore, you will not have this thing also. Good. Now we need to before developing this equivalent circuit, now we need to just think of now we are thinking that rotor is held stationary and and I have this it is more or less like a 3-phase transformer with the secondary 3-phase transformer, and you know what is its equivalent circuit, this we do not show. So, I am removing this. Secondary short circuited. So, you can see that this is the starting point, right, this is the starting point and a large current would be drawn, Xm is smaller than your Xm here is smaller than your transformer, and the leakage reactances are going to be higher, this X1 and X2 dash are going to be higher. Why? Because of the air gap, all the flux will not cross through, right. So, it will also just close it like this without crossing it over. So, the intervening air gap causes this to reduce and this to increase in this equivalent circuit, and this you could say as the single phase equivalent circuit of a induction motor on standstill, and it is worrisome, it is bothersome because of short circuited rotor winding. So, large currents will flow through the large currents you expect to be drawn from the supply. Now, if there is a 3-phase voltage which is induced in the secondary winding, because it is like a transformer. So, voltage is there on the 3-phase voltage is there on the primary side, it will induce 3-phase voltage on the secondary side, and these voltages are A phase rotor distributed winding is having A phase voltage, B phase distributed winding is having B phase voltage, and C phase distributed winding is having C phase voltage, and this is short circuited. So, what will happen? This is like, think of this is my E2 and this is my R, this is my R2, this is my JX2. Immediately a current I2 will flow, which is E2 divided by JX2. This is what is going to cause the large current to flow through this, and when this current flows, a similar thing will flow with a phase displacement of 120 degrees lagging in the B phase winding, and similar thing will flow with a phase displacement of in the C phase winding. So, it will also flow in the C phase with another 120 degree lag from the B phase, and so these 3 currents IAR, IBR, ICR will set up a rotating MMF wave in the rotor winding. So, the stator winding had already a rotating MMF wave, and now a rotating MMF wave, because of the identically distributed nature like stator windings for the rotor, a rotating MMF wave will be set up in the stator. Now, if I take away the hold on the rotor, what will happen? Like for example, I am holding a stone here in the air and I take away my hold from the stone. What will happen? The stone will fall. Similarly, if I take away that hold which I am holding on the rotor and not allowing that rotor to rotate, suppose I let it go, then what will happen? The rotor will start rotating. Why will the rotor start rotating? Because of the Lenz's law. The currents which are flowing through the windings, this is the rotor winding. Suppose the currents which will flow through these rotor windings will be such that due to the BIL principle the force will act, right. The stator has created a field, the rotor conductor is carrying a current going through it, the conductor is carrying a current going through it. So, this B of the stator, or the net B really speaking, whatever is the net B, but this B will interact with the I, the B which is present there will interact with the I and set up a force F, and on the two conductors the currents are in different direction while the B is in the same direction. So, therefore, the force will be in the opposite directions, and therefore, it will create a rotational torque, and this rotational torque will try to reduce the rate of change of flux seen. It will try to reduce the rate of change of flux seen, and so the rotor will start spinning in the direction of the rotating MMF wave which is created by the stator. Now, suppose rotor is spinning, at speed omega m. Okay. So, let me first define one quantity called slip, which is defined as omega s, the synchronous speed, minus omega m, the rotational speed, divided by the synchronous speed. This is to say how much it is slipped, how much is the rotor slipping back with respect to the stator rotating MMF wave. This S, which is a per unit quantity, a unitless quantity, is a measure of how much is the rotor slipping back from the rotational MMF wave of the stator. So, when the speed of the rotor is 0, the slip is 1. When the speed of the rotor is same as that of the synchronous speed, the slip is 0, and for rotor rotating anywhere between synchronous speed and 0 speed, the slip will be between 0 and 1, and it cannot, if it is a motor, it will at most come to the synchronous speed, right, because it is when it comes to the synchronous speed, it will catch up. It will catch up with the stator rotating field. If it catches up with the stator rotating field, what will happen? The rate of change of flux seen by the rotor will be 0. The MMF wave of sinusoidally distributed flux wave MMF wave created by the stator is moving at synchronous speed. Now, if there is a coil on the rotor and so the two conductors opposite ends are there and they are also rotating at synchronous speed, then they always see the same flux coming from the stator. So, if they see always the same flux coming from the stator, what is the rate of change of flux? It is 0. If the rate of change of flux is 0, what is the induced voltage? Even that induced voltage is also 0. So, therefore, there will not be any current seen in the rotor. So, if the rotor rotates at synchronous speed, then E2 the voltage will go to 0. So, the I2 will also go to 0 and this is no load ideal conditions operation. Ideal conditions means resistance, friction, windage, losses associated with the rotor are all these mechanical are neglected, and then if I do not connect anything onto the rotor, allow the rotor to spin, the rotor will latch on in the steady state operation, the rotor will latch on and come to the synchronous speed. In the steady state operation, rotor will latch on and come to the synchronous speed. The current inside its winding will go to 0 and perpetually it will be spinning at the synchronous speed. Now, if there are some friction or windage losses, if there are some friction and windage losses, then what will happen? To overcome that, some torque is required. So, these friction and windage losses are creating some retardation or retardation torque, and to overcome this, so much torque has to be built in the rotor winding sitting in the air gap, and when these two become, the retarding torque becomes same as the accelerating torque, I will call it as accelerating torque. When it becomes same as the accelerating torque, then at that reduced speed is the equilibrium speed at which the rotor should run. So, it has to in practice, even at the no load, it has to slip back a bit, a very small amount, but it has to slip back a bit, so that the currents. So, now what is the frequency of? So, now what is the frequency of? Suppose rotor is rotating at omega m, then what is the frequency of induced voltages in the rotor winding? So, rotor is rotating at omega m, the rotating MMF wave created by the stator is rotating at omega s. So, the relative angular velocity between the two is omega s minus omega m, which can also be written as s times of omega s, s times the s is the slip times the omega s. So, it is as if the observer sitting on the rotor will be seeing that the stationary wave the MMF wave of the stator is rotating with respect to it at a speed of s omega s. So, therefore, in this d lambda by dt V equal to d lambda by dt, usually d by dt lambda operator we replace it by e to the power j omega s, but now we will have to replace this d by dt operator by e to the power j s of omega s of t. We will have to replace it by j s of omega s of t. In other words, the frequency of induced voltage will be s times of omega s, because the rotor itself is rotating at 1 minus s times of omega s. if the induced voltage in it is at the frequency s times of omega s, then with respect to a observer stationary observer on the stator, this whole thing will create a MMF wave which is rotating at omega s with respect to observer on the stator winding. It will create something which is rotating at the this thing. So, this is additional information now that I have provided you. First information that I have given to you is that in the rotor the MMF voltage induced will be of the frequency s omega s, and therefore, the EMF induced now will not be E2 but SE2. Where from did this come? This came from the fact that RMS voltages induced in the transformer windings are given by 4.44 F N2 phi m. Now, the relative velocity between the stator and the rotor is only, so this is normally Fs, but now it is only slip times of Fs. So, therefore, the voltages will be 4.44 S Fs N2 phi m, but 4.44 synchronous Fs into N2 phi m is nothing but E2. It has to be scaled down by S. So, therefore, the current voltage induced in the secondary winding will be S times of E2, and if this is the voltage, then the reactance seen, effective reactance seen will be S times of X2, where X2 is the reactance of the leakage reactance of the rotor winding at the synchronous speed. Then at slip S, only reactance seen is S times of X2, because X2 is basically X is omega L. Omega has come down from omega S to it has come down from omega S to only S times of omega S. So, the reactance X2 has also come down to X times of X2, and the resistance of the winding remaining same, which is R2. The current will become, this will become my I2, which I can also write it as, write it as J times of R2 by S plus J times of X2. So, it is as if the resistance, because slip is between 0 and 1, R2 by S is a quantity which is larger than R2. So, it is as if the resistance has increased by R2 by S, and resistance of the rotor winding, load connected to the rotor winding or resistance of the rotor winding has increased to R2 by X, and this will be the new value of the current I2. This I2 is at frequency S of omega of S. It is at the frequency S of omega of S. Now, according to the transformer MMF balance principle, it is not exactly N1 I1 minus N2 I2 to be equal to 0 as we had with the ideal transformer, but it is now that it has to be equal to something more finite, because of the reactance of the air gap has come into this thing, but it still has to be, this balance still has to be retained as per this relationship. So, if the I2 has increased, then it has to be reflected with a corresponding increase I1 in the stator side. The compensatory current has to flow on the stator side as well, and that stator current will be at frequency omega s. It will not be at frequency s omega s, it will be at frequency omega s. Do you see why? Because the rotor MMF wave is rotating at a frequency s omega s relative to rotor, but the rotor itself is rotating at s minus this is the speed of the rotor. So, with respect to stator, this rotor MMF wave rotates at omega s speed. So, then if it is rotating at omega s speed, when I look at this d by dt of lambda, what is the induced voltage that it creates in the stator winding? It is at from frequency, I still have to replace d by dt to by e to the power j omega s of t, because the stator is seeing a relative velocity still of omega s of t. So, therefore, if the voltages are this rotor MMF wave creates a voltages at the frequency omega s in the stator winding, what are the current what is going to be the frequency of the current in the stator winding? The frequency of current in the stator winding will be still at omega s, it will be still at omega s. So, the reflected currents of this rotor will be still at the frequency, synchronous frequency on the stator side. I think this is some concrete level that we have reached, and so now we basically just need to connect these primary and secondary windings together. And what we do is this x1, this is my primary equivalent circuit, and now I will directly write this as R2 dash by S, referring it to the primary, x2 dash by this as this, and just connect it like this. So, this is the equivalent circuit of the secondary. Here I had just R2 and X2, now I have put dash and dash because I have referred to the primary, and I am very clear that even though this side even though here the frequency of I2 was on s times of omega s, when I reflect it according to the MMF balance principle of the transformer on the primary side, its frequency will be restored back to the omega s. So, therefore, I can directly now connect this across it with the reflected current which will flow here still being at the synchronous frequency. So, this becomes a equivalent circuit of a generalized transformer, also called as induction motor, at slip s, at slip s, and this is a lot of movement forward. We will have more discussions continuing forward in the next class.